My name is William Elliott and this is Matthias Elliott. Together we have developed the fluid space drive. What is a fluid space drive? A fluid space drive is a working method for propelling spacecraft for enormous distances without expelling mass, what has been called propellantless propulsion. It is relatively low-tech. Anybody can build and test the fluid space drive at no great expense, and some people already have. It presents a technology that permits us to begin considering sending probes to other solar systems now. We shall now show how the fluid space drive works. First, the parts of the fluid space drive. We need a pressurized cylinder, a mass that can move freely, the length of said cylinder, a series of flaps on the mass. Inside the cylinder there is a ramming piston at the front and rear. Here we have the cylinder. The cylinder is pressurized with air at normal pressure and temperature. Inside the cylinder, the mass M1 can move freely from the front to the rear of the cylinder. The mass has a series of flaps that, depending on their position, open or close, will offer minimum drag or act as an air brake. And we have ramming pistons at the rear and forward end of the cylinder. We shall now see how it works. In order to simplify this explanation, we will assume that the cylinder or spacecraft and the free-floating mass both have a mass of 100 kilograms. For a more accurate representation of the cycle, please see the web link in this page. We have two cycles. In cycle 1, the mass travels from the rear of the spacecraft to the front of the spacecraft. In cycle 2, the mass travels from the front of the spacecraft to the rear of the spacecraft. We start with the mass positioned at the rear of the spacecraft against the ramming piston. The rear ramming piston gives the mass a 100 Newton push. Therefore, the mass has an acceleration of 1 meter per second in the plus x direction. As for every force, there is an equal and opposite force. The ramming piston, therefore the spacecraft, also receives a 100 Newton force, but in the minus x direction. Therefore, the spacecraft receives an acceleration of 1 meter per second in the minus x direction. In this time period, the spacecraft is traveling in the minus x direction at 1 meter per second, while the mass is traveling inside the spacecraft at 1 meter per second in the plus x direction. Notice that the flaps are open. There is no air brake effect. The instant that mass M1 collides with the front or plus x side of the spacecraft, it exerts a force of 100 newtons. This is because the velocity the mass is traveling at the moment of collision is exactly the same velocity the mass was traveling when it was given the push by the rear ramming cylinder. So we end cycle 1, where the mass traveled from the rear of the spacecraft to the front of the spacecraft, with a net velocity change of 0. The spacecraft is not going anywhere. Now we shall see cycle 2, where the mass travels from the front end of the spacecraft to the rear of the spacecraft. We start with the free-floating mass at the inner forward end of the cylinder in position by the forward ramming piston. The forward ramming piston gives the free-floating mass a 100 Newton push. This gives the free-floating mass a 1 meter per second acceleration in the -x direction. Therefore, the free-floating mass will begin its travel from the +x position to the -x position with an initial velocity of 1 meter per second. As for every force there is an equal and opposite counterforce, the ramming piston receives a 100 Newton force F2 in the +x direction. As the ramming piston is attached to the spacecraft will receive an acceleration of 1 meter per second in the +x direction. This is where we close the flaps, creating an air brake. This results in a drag force Fa that in the +x direction slows the free floating mass's relative velocity. When the mass collides with the spacecraft's rear end, it no longer has a velocity of 1 meter per second. It has decreased due to the air drag. The mass's final velocity at collision, F1F, is less than 1 meter per second. Therefore, the force that is exerted against the rear end of the spacecraft is less than 100 newtons. As the force F2 exerted against the front end of the spacecraft is larger than the force S5 exerted against the rear of the spacecraft, we have a net gain in velocity. Therefore, we finish the cycle with an acceleration in the +x direction. Every time we execute cycle 1 from -x to +x, there is no velocity change. Every time we execute cycle 2 from +x to -x, we have a velocity change in the +x direction. For every second cycle, the spacecraft gains velocity. We have constant acceleration. That means that if we have two space probes on the way to Mars, one with the fluid space drive and another without the fluid space drive, the probe without the fluid space drive will travel at a constant velocity, coasting until it reaches its destination, while the probe that has a fluid space drive attached to it will continue with a constant acceleration, gaining velocity each time interval. If I had to mention only two characteristics of the fluid space drive, it is these. 1. It works. 2. It is low tech. It is so low tech that you can test it if you wish. In fact, please feel free to test it yourself, either by the methods I suggest or other ones that you may design, and test the proposal to prove it or disprove it. Thank you very much for watching.